Right, nice. Write your steps. Number one, define the variable. Number one, define the variable. Right, so whatever you're using, if it's age or whatever you're using, right? Step number one, define the variable. Is exactly the same thing I gave you last class, right? Define the variable. Number two, state your H0 and your H1. State your H0 and your H1. Number three, state the distribution that's being used. Right? Remember, you put your null hypothesis first, then you alternate, right? Right, state the distribution being used. What was 4 again, Darian? Right, by the way, remember your state the distribution used. I want to specify this according to H0. What's number 4, Darian? Now, before that, right? You have to state the level, like if it's a 5% level, and right after you state the level, you have to after you state the level, like type a test, right? The chi-square was one test we do all the time. Now we have 3 different type of tests that we can do. If it's normal, we can do that's called a upper tail test. That's like upper tail. This is the upper tail test. So it means the critical region will fall in there. It could be a lower tail test. Right? How you know what type of test you're doing? Everything comes from that H0 and H1. Right? I'll do an example and you will see how to choose it, right? So you have your upper tail test and your lower tail test. And sometimes it could be a 2-tail test. So we could test and see if a critical region here or if it's here. Right? So you have 2 critical regions here. This is called a 2-tail test. Right? There's a lower tail, upper tail test. So like if a question is like more than, it gives you an idea of where to move. Okay? That's step number 4. What's step number 5, Amber? What is step number 5? Right? After you state your level and type of test. Amber. Amber, you on red or? Yeah, okay. Amber. Yeah, 10 degrees. Amber. So you're not sure something now? Amber. Okay, all right, Amber. We'll go with Darian, right? Darian said after you do this, you have to determine the critical or rejection region. To determine the rejection region. Right? Like in the chi-squared. In the chi-squared, we learned that the rejection region is here. Right? What is 6? Let me have killing. But what is 6? We know the rejection region, right? So what is 6? Oh, calculate. Okay, that's 50% there. Calculate what? Calculate the value that you can check and see if it lies here. Okay, all right, I'll take that. So what you're gonna do is calculate the probability required. Right? So you're gonna calculate the probability required and see if it's in the rejection region. Right? We kind of call that a calculated value. And then we compare and we make our conclusion. Right? Those are the 7 steps that we need to do. Diane, say that way. So what is the test statistic? Right. Well, in chi-square, the test statistic was step number 6. Right? That was the value you work out, and you're going to compare against the critical region. You're going to check and see if that value falls in here. Same thing. We just call the probability now. Okay, sir? Okay, sir. Let me see who has made it last today. Bradley, hopefully Bradley, listen, Jesse. Hey, we ain't too bad, man. We're going to be sure you're there. All right, nice. Okay, so here's the hard thing, Olia. They're going to give you a question, and based on the word in the question, you have to figure out what type of test it is, right? So I'm just going to give you some key pointers to have an idea of what type of test it's dealing with, right? Right, so just make a note. If H1 involves a more than H1, H1 is your alternate hypothesis. If your alternate hypothesis involves a more than sign, you're using an upper tail test. You're using an upper tail test. Right? Of course, you can figure out lower tail, right? If your H1 involves a less than sign, H1, if your H1 involves a less than sign, then it's a lower tail test. So you're looking at H1, right? If H1 have a less than, then we're doing a lower tail test. If H1 have a more than, we're doing an upper tail test. Question. What do you think H1 has to be for it to be a lower tail, a two-tail test? What do you think? What do you think? So here's a H1 carries a more than. Here, H1 carries a less than. What do you think H1 has to be? Let's see if anybody's thinking. In between the two, what I mean, Darian, in between two. I say in between the two. Right, no, but it wouldn't be equal, right? Because equal is generally what your null hypothesis is, right? Your null hypothesis is generally the equal. So your H1 will be not equal. So if you see it not equal means it could be less than or it could be more than, right? Not equal means that it could be less than or more than. All right. And once you develop that, you do your little thing. And then when you do your thing, you get out, you get out, you get out. Right, Jaden? Right, Jaden? Jaden, must pay attention, eh? Bradley, are you there? Right. Most of the things that we're going to do are for the normal distribution, right? So if you have your notes, I'm hoping and praying you have notes. Just take a 2 minutes and just look back at how to read the normal distribution of this, right? Because we're gonna do one. Just look back at how to read it and how to find the probability, look back at standardization and thing, right? All right, so we're gonna try one. All right, take a little read. Part of the question missing, so I just go and write it in here for you, right? A little piece missing. All right. So I got a little handwriting there, right? Let's zoom in a little bit again. So we're gonna go through it step by step, right? Right. So let's read it first. Each year, students throughout the country set a test. Sorry, each year trainees throughout the country sit a test. Over a period of time, it has been established that the marks can be modeled, very, very important. The tests are normal. So just like in TICE, when you're doing like confidence intervals, sometimes they will not tell us are normal. They wouldn't give us standard deviation. They might give you a small sample, right? So we sometimes you have to figure out, am I using a Z? Am I using a T? Do I have to apply central limit theorem and so on, right? But the same principles once you understand these 7 steps. Right? Over a period of time, it has been established that the marks can be modeled by a normal distribution, mean 70, standard deviation 6. Right? So the H naught always comes from the population. See, they gave us the population mean there, 70. That's really important, right? This year, it was thought that the trainees from a particular county, did not perform as well as expected. The marks of a random sample of 25, so N is 25, from the country was scrutinized, and it was found that the mean mark was it was found that the mean mark was 67.3. So they found that the mean mark was 67.3. Okay, so we'll talk about what that means just now. So here what I want to do. At the 5% level, does this provide evidence of the trainees from the county did not perform well as expected? All right, that's hard, right? But I mean that they want to know based on the evidence, right? Did the county perform as expected? Okay, so the hardest things in these questions is to figure out H1. Okay, so let's start it up. Step number 1. If you get lost anywhere, stop me. So please pay attention. What is X? We have to define the variable. If you look at it here, the variable looking like basically the mark of the trainee, right? So the variable is the mark of trainee, right? Because that's what they're looking at, like the average mark of the trainee, right? Next, the H naught. Your H naught will always come from the population. So your H naught is mu is equal to 70. Right. H1 now. That's the hard thing. Right? So mu being 70 is what you expect. Right? This is the expected performance. Right? Now, H1 will be the trainees have not performed as expected. Right? This is not as expected. So about question, right? What do you think am I going to write there? Am I going to write mu is less than 70, mu is more than 70, or mu is not equal to 70? What do y'all think? Good job, Tarion. Everybody, I need an answer because there's the hardest thing. They want to know if the trainees performed less than expected, not. I'll say the answer, sorry. Anyway, so they want to know if the trainees did not perform as expected. So think about it. If they got 70, that means they perform as they expected, right? If they get 72, then they perform good. They perform as expected. So therefore, for us to test if the did not perform as expected, we will have to test mu as being less than 70. That making sense? Equal to 70 means they do real good. Or they do as expected. More than 70 means they do real good. What do you all think? Online, anybody, message, Robin Sharp. One second. Yeah, just find a cat. I thought a mouse in the school is a cat in the school. Sorry then. I don't feel something. Something value, not cut right here. All right. What's the line where? Christopher? Which line there? You all there still, right? So that was, we now reach step 2. Now we're going to figure out the distribution according to H naught. last line you wrote in the question, or it was, does the evidence, sorry, at the 5% level, at the 5% level, does this provide evidence that the trainees from the county did not perform well as expected? Right, now for the important parts. Distribution that we use it. Remember, all the data came from a normal distribution with mean 70 and variance 6 squared. Okay? Mean 70 and variance 6 squared. So remember, we are testing mean. So we're using the sample distributions of mean. I just writing it back for in case you forgot. Mean is mu and variance is sigma squared on n. Okay? So the distribution that we actually using will be x bar follows a normal, mean 70, 3 squared is that will be 36 on n is 25. Right? Everybody okay with that? That is our new sigma squared on n, right? 36 on 25. Yeah, okay. That's step, next step now. Everybody okay with X bar, right? Now, we need to state the level and test, which real easy. The level and test is step 4, right? The level is 5%. I gave it up, right? And what type of test is this, Amber? What type of test is this? Upper tail, lower tail, two tail. What type of test is this? Lower, very good. So I'm just shading it here for you. It's a lower tail test. Okay? It's a lower tail test. Right? So we're using a lower tail test at the 5% level. Okay, let's state our rejection region now. You'll have to go to a table, right? Just pull up a table coming up this. Right? So what we have to do now is to use the Z value that will give, oh, sorry. It's a lower tail test, right? So we have to use the Z value that will give you 0.05. Okay, so we have to figure out down here, if you remember, we have to figure out this Z value here. It will be a minus, it's on the left side. We have to figure out that Z value that will give you 0.05. Okay, so if you remember, go to tables, right? Remember, this left-hand side here is the same as this here on the right-hand side, right? So you have to read off 1 minus phi of whatever Z is. Right? That'll be equal to 0.05. So it means that phi of Z is 1 minus 0.05. So technically, you have to read off phi inverse of 0.95. Right? Go to tables and tell me what that corresponds to with Z. 0.95. Go to tables for 0.95. I know you would have learned those things before. But that's tell me what you get now. Just a practice of going back over the table. How much? 36.42. You sure? Yeah, yeah, I know you made a mistake there. Yeah, check back. That should be 1 point something, 1.6 something. Right? You should have gotten 1.645. Right, yeah, that's correct. But remember it minus. Why it minus again? Bradley? Why it minus again? Why is it minus? It's on the left side, right? It's on the lower tail side. Yeah, which Bradley was paying attention. Oh, how I wish you was paying attention. Right? So it could be like that. So basically, what we did here is things that we did before in the normal distribution, right? So if it's an upper tail test, lower tail test, you do this. If it's a two-tail test, though, remember you have to have 5 and 5 on either side and 90 in the middle. So you have to be careful what you're reading off, right? Anyway, so good. So the value is minus 1.645. And that's the reason because I don't have much more space, right? So what is our critical region? The critical region is we reject H naught if our Z value is less than minus 1.645. Less than, right? The reason why it's less than because the lower tail test. The reason why it's minus is because it's a lower tail test, so that's the left side, so the value for Z must be negative. So that's our rejection region. If the Z value we calculate now is inside there, we reject. If it's outside, it means it's bigger than that, because we are 10. Right, next we want to get our test value. This is the value we're going to test it at. Right, our test value, if you remember your formula, that will be X bar minus mu naught. Mu naught is the H naught value. X bar is the value from the sample all over sigma on root 10. Sorry. Divided by sigma. That was the original value that we had, right? But we like some people write it like this. Sigma on root 10. So it reminds you to put in your old sigma and put in the old root 10. Okay. So we'll end up with around out of space, right? All this. So I just squeeze in the Z value here. X bar was 67.3. The H naught, sorry, the mu naught value is the original value tested again 70. Sigma will be a 6, right? That's from here. And your root n will be the square root of 25. We'll go that from some people, instead of writing sigma on root n, they work out this. They work out 36 on root 25 and square root it. Okay, and that's the value that will go for sigma. But the reason why I like to write sigma on root 10 is to remind you to use the old sigma and use the old root 10. Okay, we'll call that from an update and what you get. It should be a minus. That's our test value. right? Minus 2.25 times. Thanks, Visha. Minus 2.25. Right? So what conclusion you'll make there, Jalen? The value is minus 2.25. We reject since C is less than. Very good, Jalen. So the last line, I can't write it all here, but here is right? Since the test value is less than minus 1.645, or you could say since the test value is in the rejection region, in the critical, in the rejection region, at the 5% level, we reject H naught. We reject H naught and conclude, well, H1, right? And conclude that it must say at the 5% level, right? At the 5% level, and conclude that the trainees did not perform as expected. The trainees did not perform as expected. Okay? And that is the way you do a hypothesis test. Any question? What's that there? So why you use that? Oh, wait. That's not. Now, wait, I missed some things earlier. So how he does know when to use chi-square distribution? The question will tell you chi-square, or the question will say test of independence. If it's a test of independence, chi-square. Oh, the chi-square is what we did last week, right? That's what we did before. If it wasn't here, you can look back at the video as well. All right. Everybody okay with this? All we have to learn to do now is to use the right distribution. If n is small, if we had to estimate sigma and so on, right? Right? As I've said, the hardest thing is to figure out H1. Right? And then we have to do different examples and we're done with volume. Right? Everything we did is just like everything that we're gonna do now. It's just like what you did in couplet intervals, the different types. All right, so let's make sure we can do one first, right? Give you our next one from here. right? I want you to follow the same steps and do this next one, please. Yeah. Anybody writing, sir? All right, next one. Better, please. Pay attention, eh? It's a 1%. It's a 1% tester, not like the last one I said, the same principle to work out the value. Right? This question, use I am giving you an X bar value, right? They didn't give you an X bar value because they wanted to calculate something called the critical value. I'll show you that after. But I want you to use this value here. Use X bar as 102. Right? You have everything else you need, right? You have mu. Mu is 100. You have n is 16. You have the level is 1%. And you have your null and your alternate, right? I want everybody to send me a hypothesis, please. I mean, send me a final answer, reject or accept. That's all I want to see. Sorry, no. I want to see a critical value. I want to see rejection region and a test value. That is it. Send a test value and a rejection region. 10 minutes, right? Let's see if we can get everybody, please. Bradley. Bradley. Watch boy, Bradley boy. Do this for me, please. Okay, everybody, yeah? Any conclusions? Three conclusions so far. Right, any conclusions? Right, good job, Jesse. Good job, Darian. Good job, Caleb. Correct, Caleb. Just waiting on the others like Jalen, Amber, Rabisha. Nice. I've seen some good things there. Right? So, right, then you specify what action this example is, right? So we can start with each node. They told us what each node is. Each node is mu is equal to 100. And they told us each one. So when I mean you to get that, you're good to go, right? As most like troubles there. Right? So that's mu is equal to 100. So originally it belonged to a normal mu 3 sigma squared, but the actual distribution x bar. Remember we use an x bar because it's testing the mean, right? So x bar will follow a normal distribution with mean 100, variance 3 squared is 9 all over n. N was 16. Okay. Next thing we're gonna do, right? Next thing we're going to do is, of course, we're going to develop our critical region. We know it is upper test. Here is 1%. So the value we have to read off for is 0.99. Positive because it's on the right side. So that value for 0.99 will be 2.576. So therefore, we reject H naught if X, if the Z value is greater than 2.576. Okay, that is our rejection region, right? If its Z value is bigger than 2.576. So next step. Next step, we are going to find the Z value, which is your x bar minus 100 all over sigma root 10. As I said, if you want, you can square root this value, take off this and put that square rooted value here. They both mean the same thing, right? Right, so as I said, x bar was 102 minus 100, sigma was 3, and it will be root of n is 60. So when you work out that, I got, what was that? I don't have that value. What that was? What was the test value there for C? Right, somebody had 2 point, no. What was the value earlier? 2.66. 0.66, all right. Yeah, all right. So that value there is 2.66, right? So the Z test value is greater than 2.576. So at the 1% level, right, we reject H naught and conclude that the mu is greater than 100. That's it. Right? That is it. I just want to talk about one more thing, right? Anybody confused? Right? Most people send something, so they were good. Jesse, all good. Dwarka sent something. Kayla, not bad at all. Not bad at all. Did Amber send something? Let's see if Amber sent anything. Which table to use? The normal distribution? If you did the normal distribution, 0.9, you look at the 0.99 and see what corresponds to 0.99. It should be 2576. Hold on, let me see if I can find one in this table again. Right, go to your normal distribution and you're trying to get 0.99, but you would recognize you can't get exact 0.99 from there. But you could get 0.9, right? You could get 0.9898. Right? Wait, and now seeing that. That's a mistake. That's a mistake there, right? Yeah. That critical value is not 2. I know saying that. It's 2.3. Hold on, huh? I think I will look at it for two tail. So it's 2.3. What's the back from it there? Hold on, I had to go back and find that now. I think it's 2.326, yes. Yeah. I think that 2.5 value is when it's a two-tail test. I mix it up. Sorry. That's why I'm not going to try to learn them. I try to learn them and I get it wrong. Okay, but it's still reject. Still reject. Right. To be honest, this question did not give you an X bar value. I just gave it to you. They wanted you to create or find something called a critical value. Right? That critical value is the X bar value that by just watching your X bar, you can compare it and say, oh, no, we gotta reject that. So if it's a two tail at 0.05 on each side, yeah. Yeah, Darian? That's what I mean. So if it's a two tail, it would be 0.05 on each side. So the value we know would be 0.995. Yes. 0.005, Darian. Right? Wait, Darren, what are you saying? So if it was a two tail test, it would be No, but it's not a two-tailed test, it's a 1%, it's a 1%, it's a 1% test, right? So whenever it's a 1% significance level, right, you read 0.99, right? And when you read 0.99, that will be 2.226. If it were two-tailed test, right? If it were two-tailed test, then here and here, you'd have to split up the 1%. So here would have been 0.005. So the value you have to read off will be 0.995. That will give you the value I had initially. Okay? I made a mistake initially. All right? Good thing it's I'm reading the table. Right. The question asks the critical value, right? So what is that critical value? If you look at this formula here, right? If you look at this formula here, if I solve x bar, I can find the critical x bar value. That's called the critical value. So if I know that the z value I'm working with is 2.326. X bar, I'm trying to find that, minus 100 all over sigma root 10. So that was 3 on root 16. And if I cross multiply, what is that? 3 on 4, I will end up with x bar being equal to 2.376 multiplied by 3 on 4 plus 100. So what I would give me is a value like how much is that? 100 and how much? 2.376 multiplied by 3/4 plus 100. How much is that? $100 and how much? Anybody can work out that, please? I demand the one to work it out. Okay, kita mabaya ka na sa Japan. I don't want to answer. Anybody, please. I beg you. 101.7. Right. 101.7. Let's see 0.74, right? So that is your critical value. If you get a sample that is more than 101.75, you know for sure you have a reject. Okay? If you get a sample less than that, well, you're upset. Okay? So just like how we could use it, just like how we could set up a critical region using probabilities, we could find the critical value and also set up a rejection region as well. Okay? So if a question asks us to find that critical, value, that's what we're talking about. Find the x bar. Some books you might see instead of x bar, they will use a C. And that's to find that critical value. You okay with that? Amber, Bradley, Darian, Jaden. Okay? So all we technically have to do now is different examples. When the sample size small, sigma unknown, we use T, right? When sample size large, we don't know the distribution, we use central limit theorem, provided we know sigma, and we're doing the same thing. Right? So it's just like critical, it's just like confidence interval. What is hard is really and truly in a question, we understand what each one is. Okay, and each one helps us figure out the type of test, and then everything smooth from there. Okay, so all we have to do a couple of examples next week, and that's it. If you all want to come out on the weekend and you want to come out and practice because the applied exam is sometime next week, you can come out and do that, right? Come on, we can practice. Yeah, it have T distributions as well. When the sample size small and normal and sigma unknown, right? Use a T distribution. So I'll do one each next week, right? Okay, do I do TikTok and watch it out, you know? Watch it while TikTok for you.